now.
Hello everyone, my name is Paria. In this presentation, I will show how to implement the solidification phase change into a multi-phase solver in OpenFOAM software. Here is the content of this presentation. Firstly, I will introduce some introduction about the solidification and the motivation behind this project. Then I will show the theory behind this implementation. Then I will show the implementations that I applied to the solver in the OpenFOAM. I will check my solver with the simple test case and at the end, conclusion and future works. Modeling phase change phenomena such as solidification or melting is important for understanding various natural and industrial systems. We can see solidification in ice formation, freezing of food, the solidification of metal casting, thermal energy storage, and crystal growth. In solidification studies, we may have two phases that liquid change to solid, or we may have three phases that we have in the freezing of droplets. You can see here that during freezing, the liquid phase changed to solid. So we have two phases of liquid and solid, and the surrounding air is known as gas phase. In the freezing droplets, the shape of the droplet will change after solidification, and also we have a volume expansion. It's better not to neglect the effect of surrounding gas on the solidification, and in this case, we will have three phases. My PhD project is about freezing droplets. So I ended up with this project of implementing solidification on a solver in the OpenFOAM to consider these three phases at the same time. The main challenge in simulating the multi-phase the problems is the tracking of the interface between phases. We have interface between liquid and gas, and also interface between solid and liquid. There is several methods to tracking these interfaces, but in this project, I have used the volume of fluid method for tracking the interface between liquid and gas, and the enthalpy porosity method to track the interface between solid and liquid. I will discuss both of these methods in the next section. And now I will mention the theory behind of this simulation. First of all, we have a volume of fluid for tracking the interface between two phases. In volume of fluid method, we have alpha, which is the ratio of the volume of one phase to the volume of the computational, say, and is defined with this step function. It's 0 in one of the fluids and 1 in the other fluid, and it's a value between 0 and 1 in the interface of these two fluids. The transport equation of the volume fraction is solved to track the interface between two fluid phases. In volume of fluid, we use one set of equations for both of the phases. For this reason, we need to consider the material properties as a mixture. And for this reason, we apply material properties with this relation to consider the properties of Y can present any properties like density or viscosity and things like this. By this way, we can consider the properties of both of the phases in the equations. For capturing the interface between solid and liquid during solidification, we have enthalpy porosity method. This method has been presented by Wall and Prakash, and they use the enthalpy method to account for both sensible and latent heat, and also they use a porosity concept to consider the interface between two liquids. Energy equation is defined like this, in which enthalpy is defined as a sum of sensible enthalpy and latent enthalpy. In the latent enthalpy, L refers to latent heat, and gamma refers to the volume fraction of the liquid when we have only solid and liquid. We're not considering the gas phase in this case. So the gamma will be 0 in solid and 1 in liquid, and for non-isothermal solidifications, that solidification occurs in a range of phase change temperature. Gamma in the interface of two phase will be defined with this relation, in which T sol represents the solidus temperature, and T liq represents the liquidus temperature, the upper and lower of the range of the phase change temperature. But we need to consider the existence of the second fluid in this relation as well. So we cannot use it as defined in this relation. Instead of this, we will use it like this equation relation, and that in which this alpha L represents the liquid volume fraction from the volume of fluid method. In this case, which we have gas and liquid, alpha L will be 0 in the gas phase and 1 in the liquid phase. So this term will be only valid in the liquid phase. By substituting enthalpy, by considering all these points, we will have this relation for energy equation. And we can see alpha L here, that will ensure that this term, which is related to solidification, will be applied only in the liquid phase, not on the gas phase. One problem with gamma in the original enthalpy porosity method that I defined here is that it needs a special iterative solution to couple between the liquid volume fraction and the energy equation. To address this problem, Rossler and Brookman defined gamma with the error function, and in this way, instead of this sharp change in the liquid fraction, we will have this continuous liquid fraction function phase change temperature range, and we don't need any iterative solution for during running the case. By substituting this relation, we will have this energy equation like this, and source term will be defined with this relation. We also have momentum equation to solve the velocity of the fluids. This is a normal momentum equation with the viscous stress terms, and that is ST is surface tension force, and this SU is because of solidification. It is known as Darcy source term, and it is applied to the momentum equation because the liquid in a cell turns to solid. When liquid in a cell turns to solid, the velocity of this liquid will reduce to zero. To address this into the momentum equation, we will add this term, and it is known as Darcy source term. Here gamma is the volume fraction in the volume fraction of a liquid that I mentioned in the previous slides. Q is a constant to prevent this denominator be zero. A Mushi is known as Mushi's own constant, and it would influence the rate at which the source term dominates the momentum equation, and its value is different in different articles, but it's something like 10 to power of 7. Now we have three phases, so we need to consider all the three phases properties in the simulation. We will change the relation that I mentioned in the volume of fluid to this to consider the properties of liquid, solid, and gas. Now I will talk about the implementations that I applied into the solver in OpenFOAM. I've started with the interfoam solver, which is a solver for two incompressible isothermal and miscible fluids. It uses volume of fluid method, and it doesn't have any phase change um, relations inside it. And here I will only mention the change that I made on this solver. And for more information about the solver, you can check the previous the reports about this in its course. Interfoam uses the immiscible, incompressible two-phase mixture laboratory library to read and calculate transport properties. It inherits from incompressible two-phase mixture to manage the transport properties of two incompressible phases, and also uses interface properties to manage the properties related to interface of two phases, such as solidification, surface tension, and curvature. And to have access to this function, the mixture object will be defined, has defined in the create field file in the solver. I changed this solver's name to solidification interform, and it is a solver for two incompressible, immiscible fluids, and it also considers solidification phase change in one of the fluids. The interform solver doesn't solve any energy equation, so it doesn't have any thermal properties like thermal conductivity and specific heat capacity. I defined this library, the my thermal incompressible two-phase mixture that inherits from this incompressible two-phase mixture to read these data from the transport properties dictionary. In this case, I need to change this immiscible incompressible two-phase mixture, and instead of inheriting from incompressible two-phase mixture, it inherits from my thermal incompressible two-phase mixture, in this case, it will have access to all the functionalities of the incompressible two-phase and also thermal incompressible two-phase. And then I defined same as interform solver, the mixture object to get access the functionalities of this library. These two libraries will be compiled separately. So we need to the solver to make the solver have access to these libraries. We need to mention them in the make options file like this. Now we need to define the properties of that are related to solidification phase change terms. I've defined the phase change properties object to make the solver to read this a file with the same name from the constant directory and read the phase change properties that we need for phase change, like latent heat, melting temperature, solidus liquidus temperatures, and solid properties. I only mentioned one of them, and the others are exactly the same, just with this dimension set that is different in each of them. You can check my report for the whole implementations. Also, we have gamma variable. I've defined it in the create fields file. It will be updated using this ER function that I mentioned in theory part, and it will be updated after solving the temperature and will be saved in time directories that we can use it to visualize our results in post-processing. Or properties that we need to consider all the three phases. I've defined the relation that I mentioned in theory part to consider the properties of liquid, solid, and gas. I mentioned just two of them, density and specific heat capacity, as an example. And now we have energy equation. The source term that I showed in theory section is defined, will be solved explicitly and added to the relation with this expression. Alpha yek here represents the volume fraction of liquid that we calculate in the volume of fluid equation. And here is the momentum equation, and here also the source 10 will be added to the equation like this. Now I will test my implementation with a test case. We have a Stefan problem that is a one-dimensional solidification problem. It has analytical solutions that solves each phase diffusion equation in each phase separately and track the interface between them. The Newman solution for this problem is shown here, that lambda here can be calculated with this transcendental equation, and STE refers to Stefan number that is defined with this relation. I defined the two-phase Stefan problem that the whole domain is covered with liquid. I used set fields to define liquid inside the domain by considering the whole domain as a liquid. First, we define a whole of it 0 and attach the 1, which means liquid, into the computational domain. Here, this wall is cold wall that is in a temperature less than melting temperature or freezing temperature. And inside the water, we have initially 4 degrees that is higher than melting temperature. This problem is an isothermal problem, so the freezing will happen in constant temperature, which is a melting temperature. But in relations, we need to consider T liquidus and T solidus. To use this, we need to define the phase change temperature range set to and a small value that I used 0.4 kelvins in this simulation. To follow the interface between solid and liquid, I used isosurface function object utility to track the temperature isosurfaces that the temperature is equal to melting temperature, which is the interface of solid and liquid. And I checked my results with the Newman solution of the Stefan problem. You can see that the freezing Foulant completely follows the analytical solution of the Newman. Then I tried to consider two phases, which half of the domain is covered with liquid and the other half is covered with air. And also I defined it with set fields that same as the previous one, just in this case the half of the domain is liquid and the other half is air. And by checking the freezing Frank evolution, we can see that it will freezing from will continue to move forward until the interface of two liquid that is 0.05 meters, and it will stop there, and it will not show up in the post-processing folder. Here is an animation of this work, but maybe gamma is not a good choice to show this the interface of two faces, but we can see that at least we can see that the interface is moving upward until reaching the interface of two faces. Can I speed up it? And when it reaches to the air phase, it happens in very less time than this, that it goes with step by step going up. So as a conclusion, I applied the energy equation and enthalpy porosity phase change model um, into the interform solver to simulate the solidification phenomenon, and I've checked my solver's validity by analytical solutions of the Stefan problem. For future works, I will work on considering density change during phase change to better detect the flow currents during phase change, and also I will consider the volume expansion during phase change to be able to apply it on the freezing droplets. This was the end of my presentation. Thank you for your attention.